Often we have a sequence, and our job is going to be to find the general formula for the sequence. So for the sequence in front of us, let's find the general formula for the a sub n. So the first thing we're going to focus in on are the signs in front of these terms. We see that these signs are alternating, starting with a -1, +1, -1, +1, and so on and so forth. Whenever you have any type of alternation, you're going to have two options for your formula. It's either going to have a -1 to the n or a -1 to the n plus 1. Since we only have two options, we can try the first option and see if it works. So let's take n and substitute 1 in there. -1 to the power of 1 is -1, and that's exactly what we want to have at the very beginning. So -1 to the n is exactly what we want. If this guy would have given me a positive number, then I would have said this is not what we want, and I would have gone with the -1 to the n plus 1. Again, pretty easy to decipher that because you only have two choices. Now for the values of 3/2, 7/4, 11/8, 15/16, we're going to analyze those guys by looking at the numerators first, and then we'll look at the denominator second. So as we're looking at the 3, the 7, the 11, and the 15, we see that all of these values are going up by the same amount. +4 here, +4 there, +4 there. And that lets me know that you have an arithmetic sequence. Whenever you have an arithmetic sequence and you want to capture that formula for it, take that number that they're going up by, take the 4, multiply it by n, and then think about what you either have to add or subtract to that 4n to have a formula to capture these values. Consider if we wanted to capture that 3. Well, our first term corresponds to n equal to 1, so if we plug in n equal to 1 for that n, then we have 4 times 1, that gives us 4. And then from 4 to get down to a 3, we would have to subtract 1. And in fact, this is the formula that captures the 3, but also the 7, the 11, and the 15. Let's try it out. Suppose that we were trying to capture the 7 from the second term. So again, this is the second term in our sequence, so n is equal to 2. Plug in a 2 in there, 4 times 2, that's an 8. 8 minus 1, that gives you 7. Yep, so this formula works. Let me encapsulate that within parentheses. And now let's focus on the denominator. The denominator is a little straightforward. So you have a 2, 4, 8, 16. I seem to recognize these numbers as 2 to the first power, 2 to the second power, 2 to the third power, and 2 to the fourth power. So in general, a nice formula for this would be 2 to the nth power. So here is your general equation for the terms in the sequence. In this problem, we're asked to consider the sequence 3n squared plus 4 divided by 5n squared plus 3. And we're going to analyze it using two techniques. First, we're going to use a table to guess what the value of the limit is as n goes to infinity. And then for part B, we're going to use a little bit of algebra to determine what the limit is, what the exact value of the limit is. So first of all, we can use a table to approximate this limit. And for part A, on one column of the table, we'll have different values of n. And in the second column of the table, we'll plug in those n values into this formula. So if n is equal to 1, we'll have 3, 1 squared plus 4 over 5, 1 squared plus 3. Right, so on the top you'll have a 7, on the bottom you'll have an 8, and you can approximate that to a decimal. We can expedite this process by using decimals. I can say that f of x is equal to the fraction of 3x squared plus 4. That's the top. And for the bottom, 5x squared plus 3. Ignore the graph for a second. And I can create a table on decimals by typing TABLE. It has x1 and y1 because often you use this for statistics purposes. For that first column, I'm going to replace it with x, and the second column, I'm going to replace that with, not that, but f of x. And if you plug in 1, it gives you 0.875, and this is, in fact, the value of 7/8. And what's really cool is that you can really expedite this process. If you plug in 2, that's like plugging 2 in for your n, and then the value of your sequence is going to be 0.6956 and change. If you plug in 3, you get this number. If you plug in 4, you get that number. So you can really make quick work of these computations. Now the question is, when do I stop? Well, from the first term to the second term, there was a really big jump, like 0.87 and change to 0.69 and change. That's a big jump. But the further I go along in the sequence, the jumps are going to be smaller. But there's enough of a change to suggest that I should go further. So from the third term to the fourth term, I see that the second decimal place has changed from a 4 to a 2. So that lets me know that it's worth my while to go further. So here's the fifth term. So from the fourth to the fifth term, I see that my second decimal place has changed again. So maybe I should go further than that. Here's my sixth term. So notice that from the fifth term to the sixth term, my second decimal place is the same. So I'm thinking that I probably have captured the value of that second decimal place. But now my third decimal place has gone from a 7 to a 2, so there's been some change there. So the idea is that you want to keep on going with these computations until you start seeing a lot of these numbers repeating. So sometimes you have to go really deep into the sequence to get a certain amount of accuracy. From what I have currently typed in, I see that from the 16th place to the 17th place, I have the first decimal place, the second decimal place, and the third decimal place values being all the same. So I'm pretty sure that I have the answer to be something in the ballpark of 0.601, and then the other numbers I'm not too sure about, but I'm sure that I have a 0.601 in my answer. So sometimes you gotta go really deep into the sequence. Let me exaggerate and just push us to a bunch of other values here. Let's see if we see it level off. I'm just kind of curious myself how many terms I would actually need. Yeah, so this particular sequence requires a lot of terms and to really start seeing a lot of, some high accuracy. So I had to go to the 88th decimal place, 88th term in the sequence to capture the first, second, third, fourth, and fifth decimal place accuracy. Okay, so on the test, I won't expect you to go that deep into the sequence. So typically you'll be working with a sequence, and maybe you're going to end up having a good idea of where the sequence is going as it goes to infinity, just with the first few terms. So I'm guessing that the sequence is headed close to something like a 0.6000, and then I'm a little iffy on the other numbers thereafter. Okay, so I'm thinking the limit is 0.6 and change. So that is my guess. But we can do a whole lot better by using algebra. So if we're considering taking the limit through algebra, whenever you're taking the limit of a quotient of polynomials, we can multiply by just the right expression to see some cancellations in our computations. So I'm going to multiply the top and the bottom by 1 over n squared, 1 over n squared. By doing this, I can take that 1 over n squared and distribute it to both of these terms. 3n squared times 1 over n squared gives me 3. And 4 times 1 over n squared gives me 4 over n squared. And this is divided by, again, 5n squared times 1 over n squared gives me 5, plus 3 over n squared. And now this limit is a whole lot easier to analyze. From the properties of limits, we can apply the limits individually to the top and the bottom, assuming that the limits exist, and they do. Because when you take the limit as n goes to infinity of 4 over n squared, you're going to have a number that you're going to have 4 divided by a really large number, so that's going to go to 0. And the same goes for that 3 over n squared on the bottom, 3 divided by a large number, that gives you 0. So these two values go to 0, and left behind you have that 3/5. And 3/5 is exactly 0.6. which is the number we were trying to capture with this table. So again, two different options of analyzing this limit, but the algebraic way definitely wins out because at best with the table method, you're going to have an approximation, but with the algebraic method, you have the exact answer. In a recursive sequence, we're given a bit of information on how the sequence starts and how to obtain the other values in the sequence thereafter. And these recursive sequences are really important. We saw how they can be used to model how much medicine is in a person's body, right? When a person is taking a certain dose every few hours. So let's revisit this type of problem by taking this recursive sequence and finding the first term of the sequence. So first of all, the first term is given. It's just 3. And for my second term, I'm going to use this formula. So my second term is going to be 3 minus 1 over the term right before. So the term right before a of 2 is a of 1. So this is equal to 3 minus 1 over 3. So 3 minus 1/3 gives you 8/3. So we have our second term of our sequence. For our third term, a of 3, we're going to use the formula 3 minus 1 over a of 2. So that's equal to 3 minus 1 over, our a of 2 is 8/3. And we can rewrite this as 3 minus 3 over 8, because this is really asking you to take the reciprocal of 8/3. So that's 21/8. And finally, for our a of 4, we would take 3 minus 1 over a of 3, and that's equal to 3 minus 1 over, a of 3 is 21/8, And that gives us 3 minus 8 over 21. So then that becomes 55 over 21.